use it to start. I'll share my screen. Right, start podcast. If you liked chapter 17 even a little bit, you're gonna love you're gonna love chapter 18.
Oh, I'm so excited.
Well, look, out of the biochem section, this is definitely the most exciting section. Proteins are just, proteins are the jam. They're so cool. Oh man, I could talk about proteins all day and all night. All right.
Just like intermolecular forces.
Just like intermolecular forces. That's right. I wake up, I brush my teeth, I talk about IMFs until I go to bed.
I stole that line. I didn't talk about intermolecular forces, but I mentioned it about something else, and they thought I was the weirdest person when I said it.
Nice. Awesome. All right. So I can't say that people don't think I'm the weirdest person, but my wife always says I got a problem because I'll teach chemistry all day and I'll get home at night, 10 o'clock after teaching for 14 hours and grab a book about chemistry. And she's like, you got issues, man. Anyhow, so chapter 18 deals with protein structure and function. And you can see right there in the title, this chapter is all about fun. All right, so with that in mind, so protein just means of first importance. It's kind of an old word. Proteins play a crucial role in biological processes. So many biological processes are regulated by proteins. And if you've ever heard of enzymes, which we've already talked about, things like lipases, right? An enzyme, a biological enzyme, is just a type of protein. So if you've ever wondered, like, what the heck is a protein? I know they're good for me. They're found in things like, meat, of course, and our hair made out of proteins. So a protein is nothing more than a polymer of an amino acid. So we're going to spend quite a bit of time talking about amino acids. So proteins have many important biological functions. So here we go. So we have enzymes, of course. I told you that an antibody that was used in that fluid mosaic model experiment, an antibody is just a protein that's used for defense. Then we have transport proteins, regulatory proteins, all these different proteins. But let's take a look at the structure of a protein. And in order to do that, we have to start by talking about amino acids, what we call alpha amino acids. So as the name implies, these compounds contain both an amine and an acid. So you should be aware of what an amine is. So an amino would look like that. And then an acid, of course, we're talking about carboxylic acids because this is organic chemistry. So we're going to see both of these functional groups in the same compound. So there are 20 common amino acids that are found in, the human body. So it says here 20 are common in nature. So if you've heard of some of them like methionine or tryptophan, those are the common amino acids. But it says here that there are hundreds that are formed naturally and synthetically. So if that would be a good question, are there only 20 amino acids? The answer is no. There are 20 common amino acids, but there are many different amino acids out there. In fact, synthetically, if you want a job, if you're looking for work, if you can make new novel amino acids, there's always a good market out there for them. People are always willing to buy a new amino acid and use it, in a potential drug. So back to these 20 common amino acids. So all 20 are what we call alpha amino acids. And if you're wondering, what the heck does that alpha mean? The alpha means the amine is adjacent to the carboxylate group. And 19 stereoisomer was, that's something that is non-superimposable on its mirror image. So let's take a look here. So more about the alpha amino acid. So it says we're going to attach the alpha carbon to a carboxylate group in a protonated amino group. So let me draw it here because I have a picture at the bottom, but I can do and make it even clearer. Okay. So it says you have a carboxyl group, okay, or a carboxylate group. So this is a carboxylate, right? Remember 8, negative charge. So the carbon that's attached directly to that, this is the alpha carbon, okay? And then it says attached to the alpha carbon is the carboxylate. So we already have that. And then a protonated amino group. So if I take an amino group, so an amino group would just be NH2, right? But it says I have a protonated amino group. So what would a protonated amino group look like? Well, let's erase this to begin with. And I would have an extra proton on there. So instead of NH2, I'd have NH3. But what do we know about nitrogen when it has 4 bonds? It has a positive charge. So there we go. So that's what an alpha amino acid is, okay? So and the reason why we draw it with the negative charge and the positive charge, if you're wondering, well, why don't you just draw it? No, why don't you just draw it like this with the carboxyl group like this and with an amine like that? Why don't you just draw it like that? Well, the reason why is because an amino group is basic, right? This is basic, right? And this is acidic. So what's going to happen at physiological pH, right? Physiological pH is around 7.4-ish, okay? What happens is that that base is going to take on the proton, right? Because a base is an H plus acceptor. And an acid is an H plus donor. So the acid is going to donate its proton to that base. So that's why a lot of times we draw the amino acid as such, where we have the positive charge and the negative charge. And there's a sassy name for that. And it's called a Zwitterion. So that's a good German word. So a neutral molecule with an equal number of positive and negative charges is called a Zwitterion. So of course, +1 and -1, they cancel each other out. So overall, the charge is 0. Now, if you think about all the people that are online listening and watching to this lecture right now, so if you think about the things that we have in common, well, we have a lot more things in common, you know, biologically speaking, than we do different, right? We have much of our DNA is similar, right? Our genetic code between all of us is virtually identical with just a few differences. But I like to describe amino acids like this. All the alpha amino acids that we're going to look at, they're all going to have this part that I've drawn up here. But what makes each one of us unique is that we all have a soul, right? So what I call the soul of the amino acid is going to be the side chain or the R group. This is what gives an amino acid its unique character, is the R group. So now we're going to look at all the different types of R groups, and we're going to classify them based off of their structure. So a little bit more about Zwitterions. So because amino acids exist as Zwitterions, okay, so let's practice writing out an amino acid. So we'll put NH3. And again, R could be a holy host of things. But because they're Zwitterions, they are white crystalline solids with high melting points and high water solubilities. So what's kind of interesting is since they're solids, you can weigh an amino acid out on a balance. It looks like a nice white crystal, easy to handle. So the two charged group, the basic amino group and the carboxylic acid, they lead to that internal proton transfer and thus produce the Zwitterion. So that's obviously a word you need to know. So what you can do is you can actually change the pH and you can affect the net charge. And if you're like, how do I do that? Well, we're going to talk about this in detail later on. But when I get to that magic pH point, so there's going to be a specific pH point where there's going to be no net charge. And when I have no net charge on my amino acid, I call that the isoelectric point. So that's the pH. That's a special pH. And every amino acid is going to have an isoelectric point. So that's a magic pH where overall all the charges balance out. So let's talk about stereochemistry a little bit more. I feel like it's been a long time since we talked about that. But what we talked about before was stereochemistry when we were looking at sugars, right? We were looking at carbohydrates. I showed you L-glyceraldehyde and D-glyceraldehyde. And I said, okay, well, they're mirror images and they're non-superimposable. Well, the same thing holds true for amino acids. So it says the alpha carbon of the amino acid is chiral. So if I look at this molecule here, this is L-alanine. Another way to draw L-alanine would be to draw my carboxyl group like this, to draw my protonated amine like this, and then to draw the methyl. So it's just a methyl group coming out here, and then I have a proton coming out like this. So you can see I have the protonated amine, I have the carboxylate, I have the proton, and I have the methyl group. So alanine has a methyl group as its R group. So when R is equal to methyl, I've got alanine. So there you go. But don't worry, you don't have to memorize the names of all the amino acids. So why is this a stereocenter? Who remembers what a stereocenter was? Well, hopefully you remember it's when a carbon is attached to 4 different groups. So I've got a carboxylate, I've got a protonated amine, I've got a methyl group, and a hydrogen. Right? All of those are 4 different groups. It's pretty obvious. So that means that this is a chiral compound. It's a stereoisomer. So the amino acid configuration isolated from proteins is L. So if you remember when we talked about carbohydrates, D sugars, so remember D glucose, alpha D glucose, beta D glucose. So D sugars, those are naturally occurring. Those are natural sugars. But with amino acids, L amino acids are the natural amino acids. And if you're wondering, well, could I make a D alanine, or a D tryptophan or something? The answer is yes. So those, like I said, there's a big market for synthetic amino acids. Anyhow, so when we draw an amino acid, we usually put the most oxidized end, or anyhow, that's just the way it's drawn here. We don't normally draw it like that at all. Anyhow, let's move on from there. So classes of amino acids. So we're going to divide them up into polar, nonpolar, acidic, and basic. So all the differences between the amino acid groups, they come from the R group, right? The soul of the amino acid. So they all have this part in common. We're going to see this in all of the amino acids. So what's going to change? It's going to be that R group. That's where the magic happens, right? So based off of that R group, the R group might be basic, it might be acidic. And if you're wondering, well, how am I going to know? Well, we're going to look at it. So some amino acids might be hydrophobic if it's got a big, non-polar tail of a chain or something. So hydrophobic amino acids can be subdivided. So we can have polar, neutral, which have high affinity for water but are not ionic at pH 7.
So
then we have, go ahead.
So if it's basic, would it still be an amino acid then, or?
Absolutely, yes.
Okay.
Because you're always going to see this skeleton. It's always going to have this skeleton. So yes, even if it's a basic amino acid like lysine, which we're going to look at in a little bit, you're right, it's still considered an amino acid.
Okay.
Yeah. Let's keep going, Sean. And I think if we keep moving past this, it'll become even clearer. So if you want to take, if you take, so all of you, I know you're all going to take organic chemistry with me in the future at UCCS. So if you take organic chemistry 1, right, so full year organic, and then you take organic chemistry 2, then from there you can go into biochem. And so it takes a lot of prerequisites to get into biochemistry. But if you get into biochemistry, one of the first things they make you do is memorize the name and the structure of all the amino acids, every single one of them, all 20. You have to memorize the 3-letter abbreviations. That's not so bad, but you have to memorize the 1-letter abbreviation. And my students, or my former students, always tell me that's the toughest thing. Now, for this class, you don't have to memorize any of the structures whatsoever. You don't have to know any of the 1-letter abbreviations, but just FYI, here they are. So let's take a look at the hydrophobic amino acids. So look, Sean, every single one, and I'm not going to highlight it in every one because that would just be funny looking, but you can see that they all have this portion, right? Every single one of these has this same bit, even on the bottom, right? They all have the same thing, so on and so forth. So what makes all of these amino acids unique are the R groups. And if you're like, well, that doesn't look exactly like what you drew. No, it's just drawn a little bit different. But again, we have the carboxylate. We have our alpha carbon. This is the alpha carbon. We have our protonated amine, right? If there's an R group, there's also a proton here. Okay, so the proton is drawn, this proton is drawn up here and all these, right? So the R group, again, that's the part that's in green. So maybe I should have drawn that in green. So this is the R group, okay? So let's take a look at all of these R groups. Now remember, we're not looking at the whole molecule, we're just looking at the R groups. Now, hydrophobic, so this is water hating. So let's take a look. What do they all have in common? Well, glycine just has a hydrogen, so nothing but that. Alanine has a methyl group. A methyl group is nonpolar whatsoever. Valine, does anybody recognize this group in green? Could you name that? There's a name for it. Like it's not like this is obviously a methyl. Who could name that part, that group in green? Waiting.
Is it isopropyl?
Damn right. Isopropyl. Let's make it more complicated. Who could name? So in leucine, could you name this one? Okay, I'll just tell you what it is. All right, so it is, this one's isobutyl. So leucine has an isobutyl, and then it gets kind of confusing because isoleucine has a sec butyl group attached to it. It's kind of funny. Phenylalanine. So if you think about it, alanine just had the methyl group on it. So when you take the methyl group and you replace one of the hydrogens with a phenyl, right? So you have phenylalanine. Proline is one of the most unique amino acids because it's the only amino acid where the nitrogen is tied into the alpha carbon by a ring like this. And so that gives it some real years where we were thinking proline this and proline that. Anyhow, then we have tryptophan. I don't know if anybody's ever heard of tryptophan before, but it's found in things like turkey. You know, they say that what makes you drowsy after you eat turkey is tryptophan. Anyhow, so tryptophan is kind of a big one. And then you have methionine. This is a sulfide because it's got sulfur between two carbons. And if you're wondering, well, what about this? There's a lone pair on the nitrogen. I have a nitrogen-hydrogen. Couldn't that, participate in hydrogen bonding? The answer is, yeah, probably to some extent. But just the aromatic ring and this other ring is just so damn big that it negates whatever effect the nitrogen has. So that's why tryptophan is still considered a hydrophobic amino acid. All righty. So with that in mind, so methionine. So again, you don't have to memorize these, but what I do want you to be able to do is to look at them and be able to say, okay, well, that's hydrophobic. All right. So, oops, I'm going to do that. Come on. Sorry, you guys, I'm really having troubles here. All right, so with that in mind, let's take a look at the polar neutral amino acids. I tried to summarize it for a class that I taught one time the easiest way I could. Anyone that has a hydroxyl or a thiol or a primary amide, those are going to be polar neutral. So you have serine, which has a hydroxyl on it. Right, tyrosine, sit in here. Yay. Anyhow, tire swing. And then we have, so see if you can wrap your head around this. This is cysteine. So cysteine has a thiol in it. And then we have asparagine and glutamine. So these both have primary amides in them. So this is just kind of a quick and dirty summary of recognizing polar neutral amino acids. Then the acidic ones and basic ones. The good thing is there aren't many acidic ones. There's only two. So we have aspartate and glutamate. So you could call this aspartic acid and glutamic acid, but the reason that they don't is because these are drawn as the conjugate bases, right? So since they're drawn as carboxylates, right? So this is aspartate and glutamate. So then the basic ones, so also you notice that aspartate and glutamate, they're related to asparagine and glutamine, right? Asparagine has one methylene, and glutamine has two methylenes. So same thing here. Aspartic acid or aspartate has one, glutamate has two. So there's some parallels you can draw there. Lysine is tough to remember sometimes, but it's got 1, 2, 3, 4 methylenes and then a protonated nitrogen on the end. I will never get you to try to memorize this one. Arginine has got this whole big spinach hanging out here at the end. We're actually going to see the structure of arginine come up a little bit more later on in chapter 21. And then histidine, if you've ever heard of histidine before, it's related to histamine, of course. Anyhow, but it's got this really interesting ring in it as well. And the reason that it's basic is you actually have two nitrogens in the ring. So there we go. So those are all the amino acids. So again, you don't have to have them all memorized, but you should be able to pick them up from a police lineup and say, okay, well, that's acidic, that's basic. There you go. That's polar, that's hydrophobic. All right, so a little bit about charged amino acids. I must be breaking some kind of rule here about text on a slide, but it says here that polar and neutral amino acids have R groups that have a high affinity for water, but are not going to be ionic. So these amino acids associate with one another by hydrogen bonding, but cysteine molecules form disulfide bonds with one another. So the whole disulfide bond thing is something we'll look at later. Yeah, then we have negatively charged amino acids. So these are acidic, and then we have positively charged amino acids, and they are basic. So let's just move on from there. Now let's get into the chemistry. We got 15 minutes or 60 minutes. But this is the fun stuff, okay? So getting into the structure and really looking at how you put them together. So remember, all of our amino acids, you should practice drawing your amino acid. So you have your carboxylate over here, right? You have your alpha carbon and your protonated amine. And then, of course, you have your R group. So here's glycine and alanine reacting to form what's called a peptide bond. So I told you that a polymer is just a protein is just a linear polymer of and this should say alpha amino acids. So what happens is the carboxyl or the carboxylate group of one amino acid, so that's here, okay, this is part of the carboxylate group, is linked to the amino group of another amino acid. So here's the amino group on this side. So the linkage that's formed between the two amino acids, this is called a peptide bond. Now, if you're looking at this and you're saying, well, come on, man, that looks an awful lot like this. And this was, you call that an amide. I remember that was on the first exam. I had to circle that and label it amide. Okay, fine. Well, when it's in a compound that's not a protein, we call it an amide. But when it's in a peptide, when it's in a protein, or when the bond is formed between two amino acids, we call it a peptide bond. So it's just a fancy name for an amide bond between two amino acids. So peptide bond. Anyhow, so this reaction is a dehydration because what did I lose? Well, it's pretty easy to see that I lost an oxygen and two hydrogens, and those are right here. So you're going to lose water. So it's a condensation reaction. All right, so let's move on. So a dipeptide. So when you condense or dehydrate, right, remove water. So from two amino acids, you form a dipeptide. So here's an example. This is alanine and glycine. So you remember alanine just had a methyl group. Glycine simply had a proton. So the amino acid with the free alpha amino group is the amino terminal amino acid, or N-terminal for short. Mr. Dion never uses this vernacular, okay? I always call it the N-terminus because it's the right way. Okay, so the part on the left is called the N-terminus, and this part over here, we call this carbon. And something is that we always write the terminus on the left and the C-terminus on the right. It's just a convention. They're always written that way when you write it a peptide. So amino acid structures are written with the N-terminal or the N-terminus on the left. So there you go. All right, so if I ask you to draw the structure of a dipeptide, oh, who am I kidding? I can't do that in multiple choice. But anyhow, there's a strategy for drawing them. So this question is example 18.1. So it says, draw the peptide of alanyl glycyl valine. So basically that means you have alanine, right? So you have alanine, and then you have glycine, and then you have valine. And trust me, I don't have all of them memorized anymore. But let me just walk you through this really quickly. So this would be way more fun if we were at Rampart Range and I was on the whiteboard. It'd be way more enjoyable. But the way you do it is this. Step one is you just write NCC, 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 right, for every amino acid. So since you have three of them, you write NCC, NCC, and NCC. Then you stick them together, okay? So you join them together. And the second carbon on each one, right, NCC, you put a carbonyl on that, right, like this, carbonyl. And then the carbon that's left over is going to take a proton, right, which is drawn here, the carbon in black. And then the R groups go on the protonated on the N-terminus and the carboxylate on the C-terminus. Now, that's the fastest I've ever explained that in my life. Normally, I make a big, exercise out of it, and we practice it a bunch of times. So what's today? Today's Wednesday. I'll tell you what, if we have time on Monday, maybe we could look at a problem where we practice this. Anyhow, but that's how you draw the structure of a dipeptide or a tripeptide. And you know what? I was speaking to some of my students at UCCS who are in advanced biochemistry, and they said, oh, on the first exam, we used your NCC technique to draw a tripeptide or something. So it works really, really well. So this is writing the structure. Just a little bit more about the structure itself. So this is kind of complicated, but I know you're all capable of understanding what the heck's going on here. But it says, recall that the peptide bonds are amide. So this is an amide, just drawn here. Now, the amides are really interesting functional groups because you have a lone pair on the nitrogen and you have a double bond between the carbon and the oxygen. So because of that, you have resonance forms. And if you remember in Chemistry 101, you might have discussed resonance forms of things like carbonate, the carbonate ion. Anyhow, we don't have time to practice resonance forms, but what you need to know is that the electrons can move around so that the amide is kind of a hybrid of this structure here, this one in the middle, and this one on the end. Now, it's mostly this one here and this one here. But if you're like, okay, what's your point? The point is this. It's about this bond, okay, between the carbon. Let me get the highlighter in. It's between the carbon and the nitrogen. That's the bond on top that's really interesting. So that bond is not a single bond and it's not a double bond, right? Because some of the time it's like a double bond and some of the time it's like a single bond. This arrow here doesn't mean anything. It's just to draw your attention to it. So because the way you could describe it is like this. It's got double bond, let me write it like this, double bond character. Okay, so it's got some of the characteristics of a double bond. And if you're wondering, like, what's your point, man? Okay, my point is just this, okay? Because of that partial double bond character, you remember that double bonds don't rotate, right? If you guys made enough models in the lab. Same thing. Because of that partial double bond character, you have restricted rotation. You have some, but it's really restricted. Basically, and what restricts it is that there's a lot of energy associated with going from S-trans, so where these two groups in gray are trans, to S-cis. And if you're like, I know what trans and cis are, but I don't know what S-trans and S-cis are. Well, the S just stands for sigma, okay? And if you remember, any single bond is a sigma bond. So this is a sigma bond. So it means that the orientation of the groups in gray here are trans, and over here on the right, they're cis. But there's a big barrier of energy in order to flip or to rotate this bond to get to the S-cis, also because of just the steric interaction of these two groups. So if you're like, well, okay, now I understand that, but what is all this? Lead to some really interesting structure for proteins, okay? So proteins aren't just shaken like a chain in the wind, you know? They have some the conformation this concept. So that is part of the reason why proteins just make some of the most interesting molecules that you've ever seen, okay? And a lot of it has to do with hydrogen bonding, but some of it has to do with this concept as well. Now, I'm not going to really pick on you about this concept, but I want you to hear it before we start looking at what's called secondary, tertiary, and quaternary structure of proteins. So there's 4 types of structure that are inherent with proteins. So there's primary, secondary, tertiary, and quaternary. You need to definitely know the difference between all, that's the worst circle ever. You need to know the difference between all 4 of those, okay? You need to know them off by heart. So let's get started and talk about the first one. Hey, I got some good news. You already know it. So the primary structure of the amino acid sequence, so when you link all those amino acids together, is nothing more than the amide bond, okay? So the amide bond, remember we had a fancy name for it, a peptide bond? That's all it is. So the primary structure is the amino acid sequence of the polypeptide chain as a result of the covalent bonding between the amino acids, the peptide bond. So the covalent bond, that's the peptide bond, or you can, if you want to call it an amide bond, that won't break my heart, okay? So each protein has a different primary structure. What does that mean? It's got a different sequence of amino acids, okay? With different amino acids in different places along the chain. So let me just tell you this. If you had alanine, so the 3-letter abbreviation for alanine, if you had alanine bound to glycine, right? And remember, if you had glycine bound to alanine, remember that we always write amino acids out in a specific way, that this is the N-terminus, and that this end has the C-terminus. This is the C-terminus, and this is the N-terminus. So my question to you is, and this might be a tough question without having looked at a lot of primary structure, but are these two molecules that I've written, are they the same or are they different?
Different.
They are. They're absolutely different, right? They're made from the same atoms. They're made from the same amino acids, but the order in which they're arranged is different. So these are actually different, very different molecules. Okay. Anyhow, this is just a bond line structure here. You can kind of make some sense out of it. So you see this is a glycine. So here's a hydrogen here. This is a phenylalanine. You can see the aromatic ring down here. Right, it's kind of written sort of funny, and you have the CH2. Anyhow, let's spend a long time on that. The next one is the secondary structure of proteins. There's two types of secondary structure, but what happens is the primary sequence of a polypeptide, what it can do is it can fold. So it folds into these regular or regularly repeating structures, and we get what's called secondary structure. So if you're ever wondering where the heck does secondary structure come from, let me sum it up for you really quickly. Hydrogen bonding. That's the answer. And where does the hydrogen bonding come from? Well, it comes from, come on, look at an amide bond, right? Not only do I have a carbonyl, which can participate in hydrogen bonding, right, with a hydrogen, I also have a hydrogen here on my nitrogen that can participate in hydrogen bonding with, a lone pair on a carbonyl. So it says here, not all regions have a clearly defined secondary structure. Some are random and some are non-regular. So this actually poses some complexity in representing this secondary structure. So there's two types. The first one is the alpha helix, and this is the most common type of secondary structure. And it's just like it sounds. It's a coiled helix, okay? And you've all heard of the double helix in DNA. Well, this is just a single helix. So what happens is you have a bunch of amino acids strung together, but once they form this helix, right, they're going to form this big helix like that. And what happens is you're going to get hydrogen bonds between atoms in different strands, or that are, in proximity to each other, I should say. So what's going to happen is each amide hydrogen and each carbonyl oxygen. So let's practice drawing our amide bond here. So each carbonyl oxygen is going to link, or hydrogen bond to an amide hydrogen 4 amino acids away. Just let me show you this, okay? So the hydrogens are parallel to the axis of the helix. The helix is right-handed. What that means is I drew it in the wrong direction. Anyhow, and the repeat distance is 5.4 angstroms, or it's pretty close, a little less than 4 amino acids per turn. What the hell? Yeah, I did draw it in the wrong way. Yeah, I did. Anyhow, so look, this is an alpha helix. Yeah, so here's my alpha helix. So you can see my spiral, and here they've shown all the atoms. What they're trying to show in this one here in B is all the hydrogen bonds. So this is a nitrogen, and this is a carbon, showing hydrogen bonds. But if you were to take your eyeball and look down in this hole, right, this is what you would see. You'd see a big empty cavity in the middle, and all the R groups are on the periphery. They're all on the outside. So that's kind of interesting. All right, and if you notice, all the nitrogens are on the inside, which is also kind of interesting. Anyhow, fascinating stuff. So why don't we stop there, since it's 7:18. So let's go back into my Teams. Sorry, let me do that. And stop